Imagine you have a set of points spread out along a plane. The problem is to calculate the distance between each pair of points using the given Euclidean distance formula and find the smallest one. This task may be relatively easy when the number of points is small, but as the number of points grows to thousands or even millions, finding an efficient solution becomes much more challenging. Finding the closest pair of points isn't just a theoretical problem. It has practical uses in many areas. For example, it helps prevent airplane collisions by identifying the closest planes in the sky. In maps and navigation apps, it finds the nearest landmarks to guide users. In biology, it is used for comparing DNA sequences to find similarities or differences. The simplest solution to the closest points problem is the brute force approach. In this approach, we calculate the distance between every possible pair of points and keep track of the smallest distance found. After checking all pairs, the smallest distance tells us the closest pair of points. The brute force method is simple to implement, but its time complexity of O(n) squared makes it inefficient for large data sets, requiring millions of comparisons as the number of points increases. This limitation highlights the need for faster algorithms in computational geometry. Now, let's explore a more efficient solution, the divide and conquer approach. This technique splits the problem into smaller subproblems, solves each recursively, and combines the results. Specifically, we divide the points into two halves. Find the closest pair within each half. Finally, we check for a closest pair that spans across the two halves. Unlike the brute force method, which has a time complexity of O(n) squared, this approach significantly reduces it to O(n) log n, making it much faster for larger datasets. The first step in the closest pair algorithm is sorting the points. First, we sort them by x-coordinates, which helps divide the points efficiently. Then, we sort by y-coordinates to streamline the process when checking the strip between the two halves. Once sorted, we divide the points into two subsets. The left half, containing points from p0 to pn divided by 2. The right half, containing points from pn divided by 2 plus 1 to pn minus 1. By splitting the points this way, we reduce the problem's complexity and focus on smaller, more manageable subsets. Next, we focus on each half separately. For each half, we find the closest pair of points. Once we have the closest pair in each half, we compare the two distances and choose the smaller one. But there's one more thing to consider. After finding the closest pairs in each half, we must also consider the strip area near the dividing line. Some of the closest points can be found here, so we need to examine the points in this area to avoid missing closer pairs. We determine all points whose x-coordinate is within the current closest distance, d, from the dividing line, and then we create an array, Si, containing these points, sorted by their y-coordinates. Next, we check for potential closer pairs within the strip. While this step might seem tricky, it's easier because the points are sorted by their y-coordinates. We only need to compare each point to 7 points, because points that are farther apart vertically are unlikely to be the closest pair. By doing this, we efficiently update the closest pair if we find a smaller distance. This check also runs in O of n time. We take the minimum distances found in both halves and the strip, then compare them to get the overall closest pair. This final step ensures we have the closest points, whether they're within a single half or spanning the dividing line. By combining these steps efficiently, the algorithm runs in O(n) log n time, making it much faster than the brute force method. This enables us to find the closest pair of points, even in large datasets, in a time-efficient manner.